Yeah, perfect. So the thing is, yesterday we saw a few things. We talked about the quantization error. We analyzed the spectrum of the quantization error, and the quantization error, we found out a new approach to look at this as if we have a sine wave input, and along with that, we have the quantization noise, and we made few approximations. So the approximations were basically um, these four approximations, which were mathematically questionable, but in the end, we know that it works in practice. So we saw the spectrum or the power of the noise, or the root mean square, or the variance of the noise, which is delta square by 12. These are some factors you need to keep in your mind. Then we had few statements. So I would like to emphasize on those statements. So basically, every increase in a bit number will increase the SQNR by 6 dBs. So basically, the reduction in SQNR by 6 dB is equivalent to noise power going down by a factor of 4, because factor of 2 represents in dBs, it's 3 dBs, and factor of 4 represents 6 dBs. So when we so basically this is when we normalize with respect to the signal power. So again, you should relate to this sentence that if we increase the resolution by 1 bit, the step size has gone down by a factor of 2, and the power of the error, which is the quantization noise, goes down by a factor of 4. So we saw that mathematically we can derive the SQNR, but for a practical or a non-ideal, basically a practical ADC, the SQNR comes out to be uh, lesser than the mathematical derived SQNR, and we saw the reason for that as well. And in the end, we also saw that the actual SQNR can be defined to find a metric. So basically, we need to qualify the performance of the ADC more in a more scientific method. So the effective number of bits is a metric to do so, and it is found out by getting the actual SQNR ratio and subtracting minus 1.76 dBs from it and dividing it by 6.02. So we saw the same idea in the graphical form. So I would like to carry forward the same idea, and basically we saw the FFT of quantized output. So then now again we have two different converters, which is a 3-bit converter and a 4-bit converter. So let's say Fin by Fs is taken care of as 19 by 4026. So this is the record length. So if this is n by 2, so this is basically 2048 over here. So let's say this is 2000, this is 1000. So what I'm about to present over here is, let's say on the 19th bin lies our input. So this is the 19th bin where our input lies, and the noise is spread throughout the broadband. But as we saw in previous video, even though we considered it as a white noise, but it's not quite white. So it's again a argument, but it was an approximation that we considered it as a white noise. But we can see that in both cases, the quantization noise is not white. If we focus on the peak of the quantization noise. So this is spreaded over a broadband, right? But somewhere we have the peak of this quantization noise. And in case of 3-bit quantizer plot, basically there is a lot of energy of quantization noise concentrated near the 450th or 430th bin or somewhere nearby. So over here, there is a lot of energy or a lot of quantization power um, concentrated. So when we look at the actual spectrum of the quantization noise, where would like the question is like where would the dominant components would lie? So the components of noise are lying throughout the record length, but we are interested in where would the dominant components would lie. So if we see the spectrum of our noise, which we saw in the previous video as well. So this is the spectrum of our noise. So basically, this corresponds to a waveform which is periodic. This was our approximation, right? And the periodic, so the period is changing from tooth to tooth. So these are the tooths, right? So it's changing, the period is changing from tooth to tooth. But on average, the period is something we are interested in. So as the step size is 2 by 2 to the power 3, let's say the signal is a sine 2 pi fn times t. So this is the signal which is input, and the slope is basically the slope of this signal. So I'm talking about this signal. So the slope of this signal is given by like taking the derivative of this a sine 2 pi fn t, which is 2 pi a times fn cos of 2 pi fn t. So basically, this is the function of cos. So then maximum slope comes out to be 2 pi a times fn. So which means the time taken to traverse one LSB will be the order of this value, which is delta by 2 pi a times fn. So if this is the time, then inverse of it is the frequency of sawtooth, which is approximately the inverse of this value, which is 2 pi fn times a divided by delta. And we know delta is 2 by 8, and the approx sawtooth frequency comes out. This is very crude and approx value. So it comes out to be pi times a times 8 times fn. So when we put the value of delta as 2 by 8, then we come around this, where Fn is basically on the 19th bin, and so the large energy or large part of the power of quantization error or quantization noise must reside around the bin, which is 19 times pi times 8 times a. So basically a is the amplitude, right? And in this case, um, the amplitude is somewhere about 0.9. So let's take it 0.9 in this case. So then this comes out to be somewhat 4/30th bin. So as we approximated over here, so the peak or the concentration of the dominant components of the noise lies near about 4/30th bin. So I can show you the plot for the same. So basically, this is the plot for the same. So we have 3-bit quantizer, we have 4-bit quantizer. So we can see the bin, which is a peak, which is somewhere around 430, 450, somewhere about this. And this is the 19th bin where our signal lies. So then, so now basically what does it tells us? So if we increase the resolution of the ADC by a factor of 2, so basically we are going from 3-bit to 4-bit. So then we see that the peak occurs around twice the 4/30th bin. So yes, when we see over here, it is somewhere around 860, 900, somewhere around that value. So someone who characterize the ADC, or a customer who use the ADC needs the plot of the FFT of the output sequence, and in many applications, the signal peak to the noise peak. So basically, the signal peak to the noise peak, that ratio is very important, and it is considered as the so basically the noise peak is also called as spurs, and this ratio is called spurious free dynamic range. So this is the spurious free dynamic range, and this is an important metric in many applications. And the dynamic range in dB is basically defined. So it's in dB. So we have 10 log. We don't have 20 log because we have a ratio. So it is given as maximum signal power a system can process while being able to give an adequate SNR. So basically, it's not overloaded. If it's overloaded, then all sorts of saturation and non-idealities are being seen. But we have considered that it's not overloaded. It is up to VREF, and the system can process while being able to give an adequate SQNR. So in that condition, the dynamic range is given by the maximum signal power by minimum signal power. So for any ADC, the dynamic range is basically given by the signal power by the noise power. And we have seen this in the previous video. So which is 6.02 times n plus 1.76 dB. So we have derived this over here last time. So this is what it is. And by this note, we have laid a layman idea on the spectral analysis of the quantization noise. So from this point onwards, we will start with OSR, basically the benefits of OSR. So in the first two videos, we talked that the oversampling ratio is basically if we take so Nyquist tells us that we need to take the sampling frequency, which is minimum 2 fin or greater than 2 fin. So we said that if we take sampling frequency too high, then it gives us the waiver, or it waivers off the complexity of the anti-aliasing filter which we are trying to make. So that was one benefit. So then we'll see the second benefit of oversampling ratio, or OSR, when it comes to the quantization of noise. So we'll see that in next video. That's all for this video from my side. Thank you so much. And if you have doubts, let me know.